So we're going to continue discussing computer science and algorithms more formally in this particular lecture. So computer science, as we mentioned, is a study of algorithms. And so here's an example of discussing something that's effectively computable. So if we wanted to write out the exact decimal value of pi, would this be an effectively computable problem? And the answer is no, because pi is an irrational number, so there's no way to express the value of pi with a finite number of digits, right? So it's not an effectively computable problem to write the exact value of pi, but you can certainly approximate the value of pi to a certain number of digits, however many you like. So let's discuss an example that goes over the requirements of an algorithm, and that they must be well-ordered, unambiguous, effectively computable, and halt in a finite amount of time. So a silly example here, algorithm from the back of a shampoo bottle. If let's just pretend that the instructions that are on the back of the shampoo bottle are related to an algorithm. So if it says wet hair, lather, rinse, and repeat, would there be anything wrong with this? So if we look at it, let's compare it to the requirements. Is it well ordered? Yeah, it looks like it's well ordered because it has all the things you would do in the right order. And is it unambiguous? And it actually, if you think about it, and if you want to look at it, uh, you know, basically at each step individually, uh, wet hair is not unambiguous because we know exactly what's going on there. But lather, what are they referring to there? They didn't say lather hair, and rinse as well. They didn't say rinse hair. Could be rinse a car or something, right? So obviously we're reading this, and we as human beings can interpret this and say and make sense out of it, but computers can't make sense out of can't have any contextual information about a set of instructions. They have to have exact instructions for what needs to be going on. And is this effectively computable? Yes, it's a doable operation, but does it halt in a finite amount of time? Well, if you look at the last step 4, it says repeat. It doesn't actually halt in a finite amount of time because it's just saying repeat, and it doesn't say what to repeat or how long or when to stop. So if you wanted to improve the algorithm, you could lay out the specifics of what exactly is going on at each step, right? And you can actually improve it a step further just to say, that we're going to lather, rinse our hair in a loop. For whatever reason, in this silly example, they're going to do it until wash count equals 2. So let's just talk about that briefly. What is wash count? And basically what they've done in the first step is they're going to say, we're going to wet your hair. And let's just pretend that these are instructions that are being sent to a robot that's going to shampoo your hair, okay? So the robot gets the first instruction that says, we're going to wet your hair. And then there's a value, or what's called a variable, called wash count, that's set to 0. And the purpose of this variable is to basically save some information or state about how many times you've actually done something or lathered and rinsed your hair. So basically, in the next step, when they go through the loop, they're going to do step 4 and 5 and increment the value of wash count by 1, which means that you've done step 4 and 5 one time. So let's keep track of that in this wash count variable and add a 1 to it, and then do it again, and then until when it's finally equal to 2, we're going to stop, and the robot's going to know that you finished shampooing your hair. So anyways, that was a brief discussion about algorithms and computing again, and we'll discuss this more in future slides. Thanks. Bye.